Okay, let's see. Good morning, everybody. Um, so let's double check here. Let's see what's going on. Let's go to our browser. And we are in Math 227. And so I want to remark here that what I did for you guys over this weekend, like I promised, is I posted the solutions for your test 2. So test 2 solutions are up online here, so you guys can go over them. Okay, here's your answers, here's your solutions. And I posted them online for you guys like I said I would. Things are graded. If you have any questions or concerns, like I communicate with you guys via Canvas and email. So I do put comments and remarks about things that you turn in. Hopefully you guys, check those things, but communication does go out on my end. So anyway, just to let you guys know, that's what's going on. So I did put those things up. Okay. All right. And then if memory serves, let's go back. We were talking about the binomial probability distribution, right? So let's see where we're at here. Okay, let's go to the iPad. So we have this web, Statistics Lecture 10, the book 5.2, 5 to 29 odd. We had assigned these things already. And what I want to remark here, the starting of this lecture, if you guys remember, the binomial probability distribution formula. So for the binomial, right, we need 3 things. N, X, and P. And remember, X is the number of successes for independent trials. And N is simply the number of trials. P is the probability of a success for a single trial. So a binomial, if you guys recall, has to do, the word bi has to do with 2 outcomes. Bi. Bi meaning 2. And there's 2 outcomes for every trial. Okay, so there's 2 outcomes. All right, now let's see, where are we at here? Okay. So 2 outcomes for every trial, and I'm going to say to you, here's where we start. And you have little p, probability of success for a single trial, and here's the complement, q, remember? All right, here's what I want to remark. Just because you have 2 outcomes, p and q, for every trial, it does not mean that they are equally likely. Remember, this is p equals q. Equally likely. When you're having a boy or a girl, right? Yes, P does equal Q. They are equally likely. Because each is 1/2, 0.5. So you said, okay, I remember this is what we work with, having boys and girls. And again, this is for a single trial. 1 trial. Well, in this case, P equals Q because they're complements. Remember that? Q is 1 minus P. Also, just so you guys know, true-false questions, if you have to guess. There's 2 outcomes, true, false, P equals Q. Flip a coin, heads, tails, P equals Q. So you have the idea that P always equals Q. And I'm going to say to you, no, that doesn't always happen. For example, if I said to you, this is something you may know, you may not know. Being right-handed, being left-handed. P does not equal Q. Does anybody happen to know why P does not equal Q? Right? Why is that? Why is P not equal to Q? Let's think about this. Does anybody know? Anybody have an idea? Why does P not equal to Q? How about this question? What proportion of the population is right-handed? Anybody know? Just because you could be right-handed or left-handed, does that mean 50% of the population is right-handed, 50% of the population is left-handed? Right? If you consider things really in a very simple way, meaning you don't include being ambidextrous, right? You don't include being able to use both. You're either going to be right-handed or left-handed. Is half the class right-handed and the other half left-handed? Anybody happen to know? Are half of you right-handed, half of you left-handed? If you were right in front of me, I would take a survey and I would say things like, okay, how many of you are right-handed? Raise your hand. Maybe you guys can take this survey now. Maybe in the comments, tell me how many of you are right-handed here. Okay, raise your hand. Put an R in the comment section, right, for being right-handed. Let's find it. Any of you guys right-handed? Put an R if you're right-handed. Okay, Cassandra. Thank you so much. All right, maybe we won't take that survey through the comment section. Yes. Guess what? Cassandra's correct. You see, ladies and gentlemen, 90% of the population is right-handed. As a probability, that's 0.90. Thank you. I see you guys. Okay, good. Here it is. I know there's a delay. I know there's a delay coming through. Okay, there's a delay coming through. And yeah, a lot of you are going to say R for right-handed. Now, how many of you are left-handed if we take that survey? If you're left-handed, please put an L. Okay, because what I want to go back to do is say to you guys that yes, the complement of 90%, right? If little p is 0.90 for 90%, then that means that Q is 1 minus 0.90, or it means Q is 10%. So 90% of us are right-handed, 10% are left-handed. This means that P is not equal to Q. They are not equally likely, okay? And yes, Joanna, that means 10% are left-handed. Thank you, guys. Okay? There's no, yes, Matt, I don't believe there's any lefties. All right? I don't believe there's any lefties here. But 10% of us are left-handed. 90% are right-handed. Okay, that's pretty good. So as you guys can see, just because you have events where there's two outcomes does not mean they are always equally likely. No, you have to consider the situation. So if I said to you guys, for example, say, by the way, I'm going to select 6 people. What's the probability? And here's what I'm going to start to do. Question 1. At least one is left-handed. Yeah, question 1. At least 1 is left-handed. Yeah, I think you're right. Now I'm going to start this lesson today with something like this, a very scary question. At least 1 is left-handed, okay? So here's what I want to say. You always let your successes be success, what's in the question. So I'm going to say here to you guys that x is going to equal the number of, well, what's in the question is being left-handed. So x is the number of left-handed people. So when they say at least 1 now, that means that x has to be greater than or equal to 1. So they're asking me this question here. It's a probability. X is greater than or equal to 1. Well, I'm going to say, what's the definition? Well, that means x is 1, or x is 2, all the way up to x is 6, which is p of 1 plus p of 2, all the way up to p of 6. Right, by the addition rule. Now, this is using what I say is the definition of at least 1, because that's our question. Now, you guys know, or should know at this point, what I didn't get into last time was using my favorite questions. But if you looked at the notes, I started to ask you those kind of questions. And this is where I'm starting with today. At least 1 is left-handed. Now, here's what I want to remark. At least 1 being left-handed here, if we use the complement rule, because notice what I'd have to do. I'm going to have to use the binomial probability formula for every one of these. And that's how you do this. Use the binomial probability formula for every single one of these probabilities. P of 1, P of 2, P of 3, P of 4, P of 5, and P of 6. So I have to use this formula that we learned last week, about maybe what? 1, 2, 3, 4, 5, 6 times. So use that formula 6 times. You're going to have to find P of 1. You have to find P of 2, P of 3, all the way up to P of 6, and then add those probabilities because of the definition of at least 1. These are all ors. You add the addition rule. Remember? However, I'm going to say to you guys, if you're awake, and you know about the complement rule, because by this time you have seen at least 1 questions over and over and over again. At least 1. So if I said to you, what's the complement here of at least 1? Can I say the probability of at least 1 is going to be, anybody know? Sorry. What do I write down? 1 minus, anybody have an idea? What do you guys think? I know there's a delay. There's a delay here. So what do you guys think here? What's going to happen? All right, Sandra. Thank you so much. P of 0. Okay. Thank you, you guys. So here's what I want to remark. Isn't it easier? Thank you, Raphael. Isn't it easier to find this value? Use your binomial probability formula now to find P of 0 in this case? The answer is yes. This is of benefit. Use the complement rule, ladies and gentlemen. And if I said to you, okay, we have to find P of 0. Okay, let's do that. But let's go back and let's note, we need 3 things for every binomial probability formula question. We need n, we need x, and we need little p. So in this case, we are selecting how many people? 6 people. And here, ladies and gentlemen, is 6. Good. X is the number of successes. Let it be what's in the question. So X here is the number, again, of left-handed people. So if they say P of 0, right here, this is the X value. So X is 0. Now, what's the probability of a success for a single trial? Well, being left-handed here is a success. So, ladies and gentlemen, for a single trial, so here's my little p now. So, be careful here. Be very careful. This is my point to you. Let X be, for our successes, whatever is in the question. So, that's what I want to remark. P does not always equal Q. And let your successes be whatever is in the question. And what's in the question is right over here, ladies and gentlemen. Number that are left-handed. So little p is 0.10. That's what we need here for the binomial. 0.10. So if all I want to find at this point, this is where my work is. I need P of 0. That's what you guys need to do. So what I always say to people, if you ever want to remember a formula and memorize a formula, every time you use it, write it down. So P of X is NCX, little p to the X, 1 minus P, which is Q in our book, N minus X. So as we seen last week, we just have to plug everything in, right? And here is 6. Here's a 6. Here's a 6. X is 0. Here's a 0. Here's a 0. And we know X is 0 here. So P of 0 is 6C0. And don't forget the value of little p. What's little p again? Let me put it in red. That's 0.10. The complement, 1 minus 0.10 is 90%. This is Q. So I put 0.10 to the 0 power, 0.90 to the 6 minus 0 power. So P of 0 is 6Z0, 0.10 to the 0, 0.90 to the 6 power. From algebra, any base of the 0 power is 1. I just need to know what 6P0 is. And for here, 6C0, we can go to the TI calculator and say, okay, TI, let's find you, TI, wherever you're at. Okay, let's clear this from the calculus course. So, enter the 6, and then we go to the math mode, all the way down to PRB, down to combination. 6C0. Hit enter. 6C0, ladies and gentlemen, is the value 1. So this number is also 1, which means P of 0 becomes 0.90 to the 6 power. So let's remember what we're doing here. we're finding the at least one question. It's 1 minus P of 0. It's right over here. So if I want to get the answer directly in the TI, right? Let's see what this is. Sorry about that. Let's see where we're at. Here we go. Let's go to that TI. So 1 minus 0.9 raised to the 6th power. This is going to give me my answer all at once. This is what I'm finding. So let's double check. Do we put everything in okay? 0.1, 90%. Looks like we're good. And here's what we get. P of 0 is approximately 0.468559. This is an approximation here. Now today, let's go out, excuse me, to our nearest thousandths again. So we can say the probability of at least one person being selected who's left-handed, 0.469. That's a chance that at least one person out of the group of 6 will be left-handed. Let's write this down, 0.469. Okay. So let's have you guys see that there. 0.469. So as you guys can determine, yes, that just because you have 2 outcomes, it does not mean that they are equally likely. So that's a question that we have here. At least one. Those are some of my favorite questions. So let's go back a few here. Let's do a few things. Some of you guys were actually pretty impressed with the TI calculator. Now, let's see if I remember here. And some of you guys, maybe on OfferUp, went out to get some of these calculators. And if you did, you know, here's what you guys can do, right? I'm going to say here's 1 minus. I'm going to do it the exact same way we're doing the above question. Second distribution. It's really vars, but it's up here in blue, distribution. You have to remember, what distribution are you working with? You're working with the binomial. You're looking for binomial probability distribution formula. See, it's A here. And once I find that, I hit enter. Now, in this example, we need to know the number of trials again. Well, how many trials are we working with? We're selecting 6 people here. And then go to the next value. Little p, ladies and gentlemen, is no longer 0.5. Little p, if you guys remember, is 0.1. Okay? That's little p. And then we go down to the next point. What is the value of x, which is 0? 6.1 and then 0. Notice this. What do? Paste that into our line. We pasted it. Now hit enter. So notice what we get. We get the exact same answer as we did before, and that saved us a little bit of time, a little bit of energy. Okay, so this is how you can go about also finding at least one. Okay, you guys okay with that? This is what we just did. All right, good. But now what I'm going to do is let's do this. This is at least one being left-handed. I'm going to say here's question 2. I'm going to give you another example. Let's write it down here. What if they said no more than 2 are left-handed? no more than 2 are left-handed. We're still selecting 6. We want to know what's the probability of selecting no more than 2 people from that group being left-handed. Well, no more than 2, if you guys remember, that means X is less than or equal to 2. That's no more than 2. So the probability that X is less than or equal to 2 is P of 0 plus P of 1 plus P of 2. And remember, this here is by definition. This is no more than 2 are left-handed. So here's where we're at, so you guys understand things here. I have to determine P of 0, P of 1, and P of 2 using the binomial probability formula. This is what we have to find. These 3 values. Maybe the complement rule is beneficial. So we're going to use this complement rule. Go back to the lecture on probability distributions. We went over the details here. The complement rule can also be used for every probability question. I mean, in theory, it could be used. In practice, it might be too hard. But in theory, yeah, you could use that formula. In theory. Practice, a little difficult. Well, here's what I'm saying. The complement rule will say to me, 1 minus the probability of the outcomes that are not here. The outcomes that are here are 0, 1, and 2. So the outcomes that are not here are 3, 4, 5, and 6. So I can subtract P of 3 minus P of 4 minus P of 5 minus P of 6. What this means here is I have to find 4 values. 4 values if I use the complement rule. And we can use the complement rule. But there's more work here. So ladies and gentlemen, the definition is quicker. The complement rule is not. So what I'm going to do here is use, my choice is going to be the definition because I only have 3 probability values as opposed to 4 that I would have to use. Now go back. Complement rule, ladies and gentlemen. 1 minus the probability of the outcomes. 3, 4, 5, and 6. These outcomes are not in the definition. Remember, 0, 1, 2. What is missing is 3, 4, 5, and 6. That's the complement rule. So I'm gonna use the definition up here. This is going to be quicker. But as you guys can see, what I do with every one of those probabilities now is I'm going to have to add those. And that's going to be some work, right? So since I know I'm using the definition, P of 0 plus P of 1 plus P of 2, we're going to have to find these things. Now remember, we need N, we need X, we need P. And still here is 6. X changes. Little p is 0.10. So X here will change. Here, this is the X value. Here's my X value. Here's my X value. So what I'm going to try to do here, ladies and gentlemen, what I think will be beneficial, I'm going to go here to my trusty TI, right? So I'm going to do this. Let me show you how this might work out really well. Second, distributions. Go down to the probability. We need the binomial probability distribution formula. That's what we're going to use. Hit enter. We still have 6. Little p is still here. We still have the value 0. I'm going to say paste. Hit enter. Now, I could do a couple of things here. Let me do it this way. Hit enter, and you say, but Mr. Judge, we got that one already. It's above. Okay, let's try that out. So if we go to the near, let's try that value out. Go to the nearest tens, hundred thousands. We said that was 0.4. Let's do this. Let's list it down here. 0.469. Let's now do P of 1. Because we already got that, right? Oops, sorry about that. That's not what it is. Good. I'm glad we punched this in. That's 0.53 to the first power. That's actually P of 0. Okay, so keep in mind, I know we did the complement, but this is 0.531. Okay, good. Now we need P of 1, right? If I go back here, just to show you, we just found P of 0. We now need P of 1. So how do I get P of 1? Do the same thing. Second, and you say distributions. Go down to binomial. Here we go. Enter. We still have 6. We still have little p. We now have to replace the 0 with 1. This is going to give us P of 1. And let's hit enter. 0.354. Okay. Round to the nearest thousands. Here's P of 1. We're now going to try P of 2. We want to get this last one, P of 2, and then we just add these values. So let's go to the TI. And second, distribution, go all the way down to A. Hit enter. We now have to just change the X value now to 2. Everything else is the same. So we're going to paste that. And we get 0.098. This is the value for P of 2. So at the end of the day here, we're going to have to add these values here, right? This number plus this number plus the next number. Add these values. So TI is here, and we can say we get 0.531 plus 0.354 plus 0.098. Ladies and gentlemen, this is our final answer. Let's double check we entered everything okay. 0.531 plus 0.354 plus 0.098, and the final answer is going to be 0.983. So let's write that down. And to tell you that all of these were really approximate, right? So we can say the probability no more than 2 people are left-handed is approximately 0.983. So this is how we can use the TI to answer these kind of questions. 0.983. Okay, some remarks here. If I go back and say to you, some of you guys are going to say, Mr. Judge, can I have done that to begin with in my TI? Meaning, here's what some people might want to do. They can say second distribution. Now, that doesn't mean you have to do it this way, but some people do. They can say, okay, start with a 0 plus second distribution the next value for x is 1 plus, again, we had 0, we had 1, now we have to have 2. Okay, close that. Now hit enter. Let's see, what do? We haven't. Oh, anyway. Okay, let's just try that again. Second distribution. Maybe I'm wrong. Maybe I'm imagining you can do that. Start with 0. Oh, that's what I did. I put a little parentheses there. No, you can't do that. Delete that. There it is. There's the error. Okay, start with 0. We'll try it again. Plus second. Just go down to binomial. Plus, now we're going to do 2. Second distribution. Okay, hit enter. Go down to 2. That's what I did. I tried to close it there anyway. Hit enter. And as you guys can see, get 0.98415. Let me write that down here so that you guys can see this. 0.98415. And this is what's going to happen now. Some people are going to look at that and go, but what's the right answer? Because now you're telling me it's 0.98415, which is approximately 0.984. Well, if you guys want to know the truth, this is more, the last answer is more accurate. And I'll explain why. This is more accurate, the last answer. The reason the prior answer is different and is less accurate is because if you go back here, every one of these answers, we cut off, we approximated these answers. We cut off a lot of values. We threw them away. And what happens is when you throw data away and you start to do arithmetic with the new approximate answers, you get further away from the exact answer. Or I should say what's better is to really use as many decimal places as possible and then approximate at the end. And that's what happened with this question here. They used a lot more data, decimal values, and they approximated at the end. This is why this is more accurate. Now, either on a test would be okay. Doesn't matter which one you use, either is fine. I just want to illustrate the process here when outcomes are not equally likely, and then you have these kind of questions that are my favorite questions. Okay, so either approach is fine. Okay, so I got my favorite kind of questions. You guys know that. No more than 2. How about if I said here, let's see if you're awake on this one. Here's question 3. Gold. Well, that looks kind of nice. Let's do the next one here. How about if we say more than 1 is left-handed? More than 1. Well, that means x is strictly greater than 1. Strictly greater. This is more than 1. So the probability that x is greater than 1, by definition, is P of 1 plus P of 2 all the way to P of 6 because there's 6 trials, remember? 6 people we're selecting. However, if you use the definition, right, this is by definition. We got 1, 2, 3, 4, 5. We got 6 probabilities to compute. We got 6 binomial formulas to use by definition. Now, let's ask you guys. Oh, let's be careful here. We don't have 6, we got 5. Because this is more than 1. Ooh, I almost made a mistake. Whew, almost. more than 1, 2, 3, 4, 5, and then another one makes 6. 2, 3, 4, 5. Okay, we got 6 probabilities because this is more than 1. Right? 2 is more than 1. 3 is more than 1. 4 is more than 1. 5 is more than 1. 6 is more than 1. 1 is equal to 1. It's not more. So if you're awake, this is by definition. I would say to you, don't use the definition. Use the complement rule. By complement, 1 minus. Remember, the complement is always, these are outcomes that are in the definition. Which outcomes are not in the definition? That are not there. P of 1 is not there. Sorry, that's true. P of 0 is not there. And P of 1 is not there. So these outcomes are not in the definition. So we're going to say 1 minus the probability of the complement of these. These are not there. So I'm going to suggest again, use the what? Which would you choose? Use your complement rule. Because we only have 2 probabilities to determine. So remember, N, X, and P. We need those 3 values. N is 6, little p is 10%, because being a success is being left-handed. And in this case, X is 0, X is 1, right? So don't forget, we're going to do this all together, right? We're going to say 1 minus each of these values all together. All right, let's try this out in the TI. Say, okay, TI, 1 minus second, or you know what? Maybe we're going to be smart here. Yeah, let's be smart. We'll verify that with the TI. Oh, no. Here's what we could do. Well, it doesn't matter. Let's be smart. By the complement rule. Do I already have P of 0, by the way? The answer is yes, I have P of 0. What was P of 0 to begin with? It's right up here. It's 0.531. So we have it. Do we have P of 1? We sure do. It's 0.354. So 1 minus 0.531 minus 0.354. If we have this data, we can do this. So let's go back and say we have 1 minus 0.531 minus 0.354. Here's what you get. 0.115. So we already had those values in our calculator. Okay, so we can answer the question if we already have known information. But what I want to show you guys here is we can still, because remember, this was 1 minus P of 0 minus P of 1. Okay, let's verify that using this information here. So we can say 1 minus, go to second, distribution, all the way down to binomial. Uh, 6, 1, remember we needed 0. Okay, hit enter. and then minus now, because I'm subtracting the complement. That's P of 0 now minus P of 1. So second distribution. And then hit now. Oh, we lost. Oh, let's clear. Delete. We got to get rid of that. You guys remember? I think it's quit. Okay, it was quit. Second distribution. Go down to A. There we go. 6 trials. 0.1, and then you go to the X value is 1 here. Close it. Oops. Almost made that mistake again. Oh. Okay. And as you guys can see, this approach gives us 0.114265. So here's 0.114625, which really is, again, approximately 0.115 to the nearest tens, hundred thousands. Okay? So this is how we could get this using the TI. Now we have Cindy saying, can we do that with a regular calculator? Well, the answer to that question, Cindy, is we actually did already. We got P of 0 and P of 1. So using the regular calculator, if you go back to the original questions of how we started this, right? We needed P of 0. We did that right here. And then later, there it is. See this? This is where we got some of this. And then P of 1, you know, you could do again as well. You can say, okay, but what about that P of 1? Well, okay, let's note what's the formula. So it looks like maybe we didn't do that P of 1. You said P of X is N CX, little p to the X. 1 minus P to the N minus X. We're trying to find P of 1 now. Right? So in this case, X is 1. N is still 6. Little p is 0.1, and the complement is 0.90. So plugging in for P of 1, we get 6C1, 0.10 to the 1, 0.90 to the 6 minus 1, which is 5. And so Cindy, any base to the first power is itself. I have to find the 6C1. And let's get a nice box. There we go. I don't know. Now I'm going to tell you what that is. That's going to be a 6. And you say, well, how do you know that? Let's clear this. 6, math. Go all the way down to probability. And we need combination. That's 3. 1. So that number is 6, like I said. But altogether, if you want to say, well, how do I find this without, I mean, you're still using the TI. But now I take 6, multiply with 0.10 times 0.9 to the 5th power. And here's what you end up with. We go to the TI, and I'll say 6 times 0.1 times 0.9 raised to the 5th power. And so for P of 1, sure enough, is approximately 3.54. Now that's not my answer. Right? That's the answer we got over here for P of 1. For P of 1, that was part of the solution. Let's go to the iPad so you guys can see it. So Cindy, this is how you could get P of 1 right here. P of 1. Here's that P of 1. And so we plugged it in. And sure enough, the final answer is you plugged it in here. You get Even though P of 1 is 0.354, here's the original question right here. This is the probability. More than 1 is left-handed, right? So probability more than 1 is left-handed, 0.115. So that's using a calculator and a TI. And like you guys know, these are some of my favorite questions, right? We have more than 1. We have no more than 2, at least 1. What if we say, oh, how about this? And am I calling these? Yeah, this is going to be number 4 maybe. How about, since we're selecting 6, less than 4 are left-handed, or less than, say less than 5 are left-handed. So now we're going to look at this and say, what's the probability that less than 5? Well, that's x less than 5. Sorry. Probability that x is less than 5, that's P of 0 plus P of 1 plus P of 2 plus P of 3 plus P of 4. This is smaller than 5. So you would need 1, 2, 3, 4, 5 computations to do if you use the definition. Now, in this case, I'm not going to use the definition, right? By the complement rule, it's always 1 minus the outcomes that are not here. 0's here, 1's here, 2's here, 3's here, 4's here. Because that's all the outcomes that are less than 5. The ones that are not here is P of 5 and P of 6. You subtract the outcomes that are not in the definition. This is using the complement. So now I need P of 5, I need P of 6. Okay, so P of 5, P of 6. So maybe we can do something like this. Maybe we'll say, well, let's note from the calculator. Let's do a calculator portion so we can kind of even this out. Right? We need n, x, and p. P of x is ncx, p to the x, 1 minus p to the n minus x. Here's my formula. Right? If I ever want to learn how to use a formula, I just write it down. So for P of 5, x is 5. N is 6 still. Little p is 0.1, which means the complement is 0.9. So for those without TIs, let's focus on this. P of 5 is 6c5. 0.10 to the, looks like we didn't, I thought we put the x power there, right? I think we did, but. And what is x? 5. Fifth power, 0.90. What's 6 minus 5? That's 1. Remember, any base of the first power is the base itself. So the real work comes here. (6c5). This is where your calculator is going to come in. Now, I know this answer. This answer happens to be 6, but let me show you how that works out. But double check. This is using the calculator for some of you guys today that don't have those TIs. This is what you'd have to do. So let's prove that to you guys. TI 84. Let's go to our calculator. 6c5. 6 math. Go to probability, go to combinations. We need combinations. There's a 5. Hit enter. Sure enough, this is 6, like I said. So, punching this in, P of 5 is 6 times 0.10 to the 5th power times 0.90, or just 0.9. Doesn't matter. So, 6 times 0.1 raised to the 5th power times 0.9, and that's going to be to the 1st power, right? So here's what we get. Now remember, this answer is in scientific notation. That means write down 5.4. And you're going to now move this 5 spaces. 1, 2, 3, 4, 5 to the left, and put some zeros. Now I'm going to say, put this whole thing down. There's 4 zeros, 5, 4. Put this whole answer down. 1, 2, 3, 4 zeros, and then a 5, 4. Because my answer's in scientific notation, right? Now, I need, this is going to be the value for P of 5. We need P of 6. So, P of x and Cx, P to the x, 1 minus P to the n minus x. Plug in these values. X here is 6, 6, 6, and 6. And here is also 6. Little p is 0.10, and the complement is 90. P of 6, 6C6, 0.10 to the 6, 0.9 to the, remember, 6 here minus 6 is going to give you 0. 0.9 to the 0 power is going to be 1. Now, I already know what this number is. I'm going to tell you guys. This is also 1. And I can show it to you. So P of 6 will be 1 times 0.10 to the 6 times 1. Or we can say P of 6 is simply 0.10 to the 6. Okay? And let's go back and let's take a look. Like I said, 6C0. 6, math, combinations. I'm sorry, 6C6. There we go. Right? Didn't we say what it was going to be? I'm saying this is 1 here. All right. Sure enough, it is 1. Okay. Here's what I mean. This is 1. We just found this value. 0.9 to the 0 here was 1. There it is. We're left with 0.1 to the 6 power right here. This is what we're going to use our calculator for. Point 0.1 to the 6 power. And then notice what you guys get when you get 0.1 to the 6 power here. This is 1 e to the minus 6 power. So don't forget, right? This is 1 with a decimal point. e to the minus 6. So I'm going to have to move this 1, 2, 3, 4, 5, 6 times. And we fill this in with 1, 2, 3, 4, 5 zeros. This is why I'm writing all of them. So P of 6 is 1, 2, 3, 4, 5 zeros with a 1. So I want to make sure this is emphasized and this is emphasized. P of 4, P of 5, P of 6. Right? There's 6 zeros there. Now you say, what's the answer? Well, go all the way back to the question. We need to take 1 and subtract those two probabilities. So when we take 1 and we subtract those two probabilities, right? So we say, okay, probability, I believe the question was less than 5, but we didn't use this. We didn't use the definition. Don't forget to write these down. Here, P of 6 had 5 zeros. 1, 2, 3, 4, 5 zeros and a 1. And then P of 5, we said, oh, we have what? 1, 2, 3, 4 zeros, 5, 4. So 4 zeros, 5, 4, and then 5 zeros and a 1. All right. 1 minus 1, 2, 3, 4 zeros, 5, 4 minus 1, 2, 3, 4, 5 zeros and a 1. 1, 2, 3, 4, 5. There we go. So notice what you get. 0.99. How many nines? Looks like it's 1, 2, 3, 4 nines, a 4 and a 5. Now they didn't say where to approximate, right? It's 4 nines, 4 5. So anyway, we can say maybe approximate here. Tenths, 100,000, 10,000, 100,000s. So this probability of less than 5 students is 0.99995. And we've been writing that in black. Let's get a nicer rectangle. Okay, 0.99995. This is the probability that less than 5 students will be left-handed. That's smaller than 5. Remember, this is out of a group of 6. So this is working with binomial probability distribution formula. Okay, this is kind of how this all works together here. But if we start the day by going back and saying things to you like, guess what? Just because you have events that have 2 outcomes doesn't always mean they're equally likely. So we started the day with the binomial probability distribution formula showing that they are not always equally likely. Okay, so we're over here. And I guess I could remark here. The other day, these are the questions that we actually work with, if you guys know what I mean, right? We did these questions. These 5 examples. Last Thursday. And I went through the demonstration of that. Boy, girl, oh, here's the detailed demonstration. It's in our notes. And then I mentioned something to you guys after the last example. I said, here, remember, these are my favorite questions. If you guys notice, what did I just do with us today? I didn't answer these questions. I gave you another example. At least one boy. Let's change the color. Let's say that's x less greater than or equal to 1. More than 1. That's x greater than 1. Less than 2. That's x smaller than 2. More than 2. That's x greater than 2. Between 1 and 3. So I asked you guys to work on these kind of questions at the end of the lecture. And hopefully you did, right? These are some additional examples. I'm going to even ask you guys to take a look at question 12. Here's an example where P is not equal to Q. And it's a classic question. It's a multiple choice question. In this setting, what you have here is a 12-question multiple choice test. What that means here is n equals 12. And what you're going to do is you're going to guess on each one of these questions. Okay? You want to guess on each one. And hopefully you guess correct. So they want to know, if you guess on every question, what's the probability that you guess correct on? So x here, ladies and gentlemen, is the number of correct guesses. It's a G. It's the number of correct guesses. So no questions. This is x equals 0. One question correct. X is 1. X is 2. X is 3. And that's not boys. That's going to say x is 4. I'm going to change that. Typo. So these are some questions I want you guys to work on as well today. Examples. Okay? And I put some information here as well for you on how to answer this question. Right? Guessing correct, we want to know right here, why is that the probability of a success? Why is that little p? Well, because of the fact that, what do you have? 5 possible answers, A, B, C, D, and E. So this should look familiar to you guys. The probability of guessing correct is 1/5. And that's little p. So you guys are started. You can get started on these kind of questions, 11 through 15. And then, of course, my favorite, and I went through how to do this in detail. And, of course, my favorite questions are the at least 1, at least 2. So x is greater than or equal to 1. X is greater than or equal to 2. More than 4. X is greater than 4. Less than 10. X is smaller than 10. And then between 3 and 8. So 3 is less than or equal to x, less than or equal to 8. So I want you guys to finish this worksheet here today. And as you guys can see, it's good practice for your homework because I already assigned homework for you guys on this. So do this worksheet. I gave you homework on the web. I gave you homework in the book. This is good practice because, as you guys can see, this all comes down to language and can you use your calculator? Language and using your calculator, okay? So anyway, this is where we're at. So hopefully you guys had a good day with this. If you have any questions, again, I'm in my office for office hours starting in about 15 minutes. And if you have trouble getting in, just email me and I'll let you in. And this is where we're at. So anyway, thank you guys so much. Have a good day and work on these things. And I'll see you guys tomorrow.